Linear regression was the model we used for regression. One of the models we discussed so far to do with supervised machine learning regression problems. Now, is there a model we can use for classification that behaves a lot like linear regression? Linear regression was a very simple model, but we saw with that very simple model we can derive some insights when we use it. So is there a counterpart? Or maybe let me throw this question at you. Can we use standard linear regression for classification? If so, why? And if not, why? We can't use linear regression as it is written for classification. And the reason why is because linear regression can return any value. The y value that it can predict can be any continuous value from negative infinity to infinity. For classification, we're not trying to predict continuous values. But what if we're able to tweak our model? We're able to tweak linear regression, this linear regression framework we discussed before. If we can tweak it such that it only predicts values between 0 and 1. Continuous values between 0 and 1. Why would that be useful? Why would it be useful if we can tweak this framework of linear regression such that it's limited to continuous values between 0 and 1? We want to do this because, as we saw before, we can go ahead and have a probabilistic model. A probabilistic model is one that's going to return a continuous value between 0 and 1. And we can interpret those values as probability. Probability to be in class 1. So we need a way we can take the output of linear regression and have it such that it's bounded between 0 and 1. So we have here is the framework for linear regression. X times beta. Remember, there's a matrix multiplication here. X is our feature matrix, rows and columns. B is our beta coefficients. 1 for each feature, plus the intercept term. We can take that output and feed it into another function. Let's feed into the sigmoid function, which is defined as 1 over 1 plus the e to the negative x. If we feed the output of linear regression to this function here, then we're going to map those values between negative infinity to infinity to be restricted between 0 and 1. So let's visualize this sigmoid function. Let's visualize it. So that's what we're going to do there. We're going to plot the sigmoid function. We're going to plot for values from negative 10 to 10. And there is our sigmoid function. And that's where it gets its name. It has a shape that resembles like an S. So in this sigmoid function, notice the x-axis. We only plot it from negative 10 to 10, but it can go on to negative infinity to infinity. But look at the y values. Look at the y values for this function. The y values for this function are capped, are not going to exceed 1 and not going to go below 0. So regardless of what value that we use for the sigmoid function, will be tossed to the sigmoid function, the output will always be between 0 and 1. So this is great. Let's take the output of a linear regression model, run it through the sigmoid function, and whatever value we get, we can interpret as a probability. So now with that additional modification, that small modification, we can take our linear regression framework and create a model to do classification. We can create a probabilistic model we can use for a supervised classification problem. This is called logistic regression. I know the name's a bit confusing. Logistic regression is a model for classification, but why does it have regression in its name? Well, the one way I like to view why it has regression in its name is because it's predicting a continuous value between 0 and 1, which we interpret as probability, in which we can go ahead and use to make classifications. So it's a very similar framework as linear regression. We have our data set X with with any number of features, that's our columns, and then a coefficient that's going to belong to each of those features. And now the task is, what are the best values of beta to choose and to use for our model? Now, for linear regression, we have to do that same thing. We have to figure out what are the good beta coefficients to use to have a line or some sort of hyperplane that best fits our data. What do we use? Let's talk about that best fits our data. What do we mean by that? What do we mean by best fits our data with regards to linear regression? With regards to linear regression, best fits the data meant the set of beta coefficients that are going to result in the lowest possible mean squared error. But for logistic regression, that's a classification, we cannot use mean squared error, so we're going to have to use a different error metric. So we're still trying to find beta coefficients, these model coefficients, in this linear framework, but we're not going to use mean squared error. We're not trying to reduce the mean squared error. We're going to reduce another metric. What metric should we use? Well, we discussed various metrics to use for probabilistic models. Logistic regression is going to use the log loss. Remember we discussed about log loss? It's a model that's going to emphasize the certainty of your predictions. You don't want to be just right. You want to be very certain that you are correct. So for logistic regression, when we use logistic regression, what is happening is that the model is trying to figure out what are the good set of beta coefficients to use that will result in the lowest cross entropy log loss penalty for our model, given the data, given the training data. Let's go ahead and use logistic regression in scikit-learn. I want to emphasize that the way these coefficients, the beta coefficients, are solved in scikit-learn is by applying gradient descent. There is no closed form solution for these beta coefficients, so when you use logistic regression, underneath the hood it's using gradient descent to figure out the beta coefficients. So let's generate some data. Now one thing, so in this example here we have two-dimensional data, so data that only has two features, two characteristics, two attributes, and we can easily plot it, we can easily visualize how our data resides in a two-dimensional space. So x1 and x2 are two features, and we have two classes, so binary classification, so class red and class blue. Now let's go ahead and use logistic regression, but we're also going to draw out or plot out what's called a decision boundary. Now a decision boundary is a boundary that's going to illustrate how the model classifies observations. We can draw the decision boundary on our space, this space where our points reside in, our feature space. And what we'll see with the decision boundary is that it'll say in these regions, the model will predict this class. But in these other regions, it's going to predict some other class. So hence the name and decision boundary. You can see the boundaries between the decisions that the model is going to make, whether the observation is class 0 or class 1. Okay, so we import logistic regression, so that's the name. We create our classifier. Let's go and fit it, pass x and y. Then let's make predictions on x. Let's print out the accuracy. Let's see what our accuracy for our model is. So we have 84% accuracy in this case. In this block of code here, we're going to construct a decision boundary. So we're going to actually calculate what is the probability of the observation to be in a certain class. So we're going to use the predict problem method. If our classifier is a probabilistic classifier, then that model will have the predict problem method. So it'll be a continuous value between 0 and 1. Let's go ahead and plot those. We'll plot it. So there it is. So now we have here, we have our original points, the blue and the red points, along with the decision boundary. So darker red colors mean a greater probability to be in class red. And lower probability values, so these bluer colors represent that the probability to predict class red is very low. So we're probably going to predict class blue given a threshold. So take a look at this decision boundary. Anything that is interesting about this decision boundary for our logistic regression? Let's consider the shape. Consider that shape, that's dividing the blue region and the red region. What is that shape? How does that shape? What is that shape that divides the blue and the red region? That shape is a line. It is a line that tries its best to separate the blue and the red points. So geometrically, what you can view what logistic regression is trying to do, if we have a two-dimensional space, if we have two dimensions for our data points, so two features, is as try to figure out where should I draw a line that best separates the data. This is similar to what we talked about linear regression. In linear regression, we try to draw a line that best fits the data points, that best goes through the data. In logistic regression, since we're trying to do classification, one way to view is you're trying to separate. You're trying to figure out what is a good boundary that's going to separate my two classes. And what logistic regression is going to do is trying to figure out a line. Where should I position this line that's going to best separate my blue and my red points? Of course, there's going to be some mistakes. It's not going to be perfect. Regarding, you can't draw a line that's going to perfectly separate those two classes. So it's going to try to do its best. And by best, as in try to reduce the cross entropy term, the log loss term. That's what's happening when you invoke the fit method, when you train this model, when you train logistic regression. So what we see here is that it's basically drawing a line to separate the points. And it's restricted to a line because it's a linear framework. So that's why logistic regression is a linear regression counterpart for classification. Just like linear regression, you're limited to a line through the data. Same thing with logistic regression. You're limited to a line to separate the points. Now, when we think of higher dimensional space, so let's say we had 3 dimensions for our features, then logistic regression will try to draw a plane that best separates the points. And we could generalize the concept of a plane, call it a hyperplane for larger dimensional spaces that are hard to visualize, understand what's going on. So we'll call those hyperplanes, those planes of higher dimensions. We'll talk about those concepts again. We talk about support vector machines. But one point here is the importance of understanding this decision boundary and the fact that logistic regression can only draw a line or a plane, some hyperplane that best separates the two classes.